Okay, this is day 11 of Advent of Code 2023. So, we have this one called Cosmic Expansion. This one was quite fun. I think I'm saying at this point that all of them are quite fun. They are quite fun. You should all do Advent of Code. It's fun. So, you continue following the signs for the hot springs and eventually come across an observatory. The elf within turns out to be a researcher studying cosmic expansion using a giant telescope. He doesn't know anything about the missing machine parts. He's only visiting this for this research project. However, he confirms that hot springs are the next closest area likely to have people. He'll even take you straight there once he's done with the observation and analysis. Maybe you can help him with the analysis to speed things up. The researcher has collected a bunch of data and compiled the data into a single giant image, your puzzle input. The image includes empty space as dots and galaxies as hashes, or pound signs for you Americans. So, there is an example input, which is not the one that I have up here, but let's just quickly copy that in. Cool, there we go. The researcher is trying to figure out the sum of the lengths of the shortest path between every pair of galaxies. However, there's a catch. The universe expanded in the time it took the light from those galaxies to reach the observatory. Due to something involving gravitational effects, only some of the space expands. In fact, the result is that any rows or columns that contain no galaxies should then be actually twice as big. In the above example, 3 columns and 2 rows contain no galaxies. These columns, these rows. These rows and columns need to be twice as big, and the result of the cosmic expansion therefore looks like this. So instead of it being 1 column here, it's 2 columns. This is transformed into 2 columns. This is transformed into 2. This is transformed into 2 rows. This is transformed into 2 rows. Yeah. So there's that. Equipped with this expanded universe, the shortest path between every pair of galaxies can be found. It helps to assign every galaxy a unique number. Blah, 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 blah. In these 9 galaxies, there are 36 pairs. Only count each pair once. Order within the pair doesn't matter. For each pair, find the shortest path between 2 galaxies using only the steps that move up, down, left, or right. Exactly 1 empty space or galaxy at a time. The shortest path between 2 galaxies is allowed to pass through another galaxy. For example, here's one of the shortest paths between 5 and 9. There we go. The path has a length of 9 because it takes a minimum of 9 steps to get from Galaxy 5 to Galaxy 9, the 8 locations marked with a hash plus the steps, the step to get to 9 itself. There are some other examples of shortest path lengths listed here. In this example, after expanding the universe, the sum of the shortest path between all 36 pairs of galaxies is 374. After you expand the universe, what is the shortest path between the pairs of galaxies? So there we go, there was my input. So what we want to do, we want to test for this. So if we just quickly do solve test input is equal to 374, and that will give us our starting point. Cool. Okay, so let's get cracking. So the first thing we need to do is define, I think, what a galaxy is. We don't have to, but I'm going to define what a galaxy is, which is a hash. And then we want to make the whole grid. So the grid is equal to string.splitlines. And then I think if we keep a track of all of the galaxies, it says that we just need to go over the combinations of the galaxies. We don't necessarily need to go over the order, over kind of all the pairs, but yeah. So if we keep a track of all of the galaxies and keep a track of all the empty rows, then the plan there is to then double the size of the empty rows as we do the calculation at the end, rather than as we go through it. What we could do is expand the rows and columns straight away. We could do that perfectly fine. However, not to think too far ahead, but when you get into part 2, that's not gonna be possible. So let's just go with doing the calculation as we do it at the end, rather than modifying anything as we iterate over it. So if we keep a track of the galaxies, if we keep a track of the empty rows, cool. So then if we get the we want to also keep track of whether or basically what all the columns are, and whether they're empty. So we'll set the empty columns later, because we'll need to kind of get some information first. But what I'm going to do is just make a list here where we can track the columns and determine if they have anything in as we go through it. And then when we get to the end, so we need to iterate over all of this, and then once we get to the end, we can then determine all of the empty columns. So false for we don't care about in grid 0. Or we could do false times the length of grid 0, or would that just do 0 multiplied by whatever, which makes it 0? I don't know. Either way, let's go with this. Cool. So then what we want to do is we want to go over all of the rows and columns and pull out everything we need. We need to determine the columns, whether they are true or not, as in whether they have anything in. We want to keep a track of all the empty rows, and we want to keep track of where the galaxies are. So we're going to pull all those out. So for our row in enumerate, we are going to go over the grid. So if the row count of the galaxy is equal to 0, then we are going to append the row, dot append into the empty rows, and then we'll just continue onwards because there's nothing else left to do with that particular row. Cool. So then for columns, for C in range 0 to, in fact, let's just go to the length of cols. So this will give us all of the, this will give us every column. So then we can just go up to that. What we want to do here is if the grid of the row and the column is equal to a galaxy, then what we want to do is say the cols C is equal to true, and add a galaxies dot append, and we're just going to give it the coordinates of where we found it. So we're saying in this part here, we're going to change this particular index of the columns to true to say something is in there. So we've set it all to false to start with to say we don't know, or there is nothing. As soon as we find something, we're going to say yeah, there is something in here. Cool. So now we've got all of these. We've got all these particular pieces we need. We've got the galaxies coordinates. We've got the empty rows, and we can now get the empty columns. So if we do empty cols is equal to C for C V in enumerate cols if not V. So basically, if the value is false, then we'll get the index. If it is false, then we'll get the index. Otherwise, we will not get the index. So now we have the empty rows, the empty columns, and the galaxy. So now we can start adding things up. So for what we're going to do here is we're actually going to use a library. I say a library, part of the standard library, but we're going to import from itertools combinations. So what this is going to do is it's just going, if we give it the galaxies, it's going to return to us an iterator of all the combinations of the galaxies, which is exactly what we want for this. We're just going to get a pair, we're going to get another pair, so on and so forth, and it just won't repeat the same combination. Cool. So what we want to do is we want to get the row, so the A row, the A column, and we also want to get the B row and the B column in combinations. We're going to pass it the galaxies, and we want pairs of 2. So then for r in range min of the A row, B row, to the max of the A row and the B row, total plus equals 2, because each of these is doubling in size. So what we want to do, where we find 1, we want to then make 2. We're going to add 2 in, and we're going to do that to if R is in the empty rows, else 1. And then we're also going to do for C in range min max. So what we want to do here is do the A column, the B column, the A column, and the B column. Then we're just going to do total plus equals 2 if C in empty cols, else 1. And we're then just going to return the total. Okay, so what have we got here? Enumerate is not defined. Yeah, that's because I can't spell. Enumerate. There we go. Cool. So let's just go into day 11 and let's do PyTest part 1.py. Excellent. So we get a passing test. So then if we just then do and Python part 1.py, so then we get 9181886, which is exactly what we got down here. Excellent. So this was part 1. What I'm going to do, just because I know what's coming in, I know exactly what's coming in part 2, so I'm just going to grab everything, and then if we just nip on over to part 2 and then paste it, let's change the test input. So part 2, so what we've done here essentially is go over the rows and say, right, where what am I thinking? So we're going over the rows and basically increasing the count, the distance between by 2 if we come across an empty row. We're increasing the distance by 2 if we come across an empty column, and we're doing that to go from, say, 5 to 9, and we're getting all of the rows and then all of the columns between these 2 points. Yeah, that's essentially what we're doing. The reason we've done it this way is because of part 2. The galaxies are much older and much further apart. Now, instead of the expansion you did before, make each empty row or column 1 million times larger. That is, each empty row should be replaced with 1 million empty rows, and each empty column should be replaced with 1 million empty columns. In the example above, if each empty row or column were merely 10 times larger, the sum of the shortest paths between them would be 1030. if each were 100 times larger, then it would be 8410. Your universe will need to expand far beyond these values. So this one, it doesn't actually give us a test value for the million, so we can't actually test it. But it's a real simple change between this solution and this solution to get the million, because of the way that we've done it. So really all we need to do, we won't use PyTest for it. So if I just actually remove if I just remove those the test, because we don't need it, what we're going to do, instead of doing 2, we're going to say 1 million, and we'll change this to 1 million. And essentially, that's the solution. Part 2. Yeah. Cool. So if we then just run part 2, I'll leave the PyTest in there for part 1. So part 2, we get 791134099634, which, as we can see, is exactly what I got here. So because over the years doing AOC, you kind of get used to spotting some patterns, and usually these sort of expansion problems of, just expand it by 2. Usually you need to prepare for a much more stupid size afterwards, which means that you could do this iteratively, actually modifying the string, modifying the input. You could do that, but when you get to this one, that is a really silly approach. It's just going to take forever. So instead of doing that, thinking a bit more cleverly about how you get to the solution can really save you when you get to part 2. When you think about real work problems, a lot of times you will be doing, a part 1. You won't necessarily know that there's gonna be a part 2. You won't necessarily know about changes of requirements ahead of time. But you start to spot patterns of requests for, we want to be able to do ABC, and that ABC is similar to what you may have seen before, and that before you've then, a couple of months later maybe, had a follow-up request for some additional features for that particular thing. You may not know that they're going to come, but you can at least preempt the possibility. So if you've seen it a few times and that's quite likely to happen, what you can do is make some changes to how you do things in your first go, so that it makes it easier for you later on to be able to expand upon, but not necessarily always spending the time in doing so, because sometimes you never will get a part 2, and sometimes it will only ever be a part 1, and that's it, and those new requests for features may never come. But you start to spot patterns for when that could happen. This was one of those ones where spotting this pattern, if you're new to it, you're not really going to know. You may first just try and modify the input. But yeah, after spotting the pattern you can quite easily tell. Doing that 1 million for every row and column, it's not going to be possible, especially when this is the size of the input, of the actual input. So yeah. Anyways, that was day 11. See you for day 12.